Um, okay, so good morning, everyone. Welcome to Stellenbosch. Yeah, it's really a pleasure to have you here and to have a focus area workshop of the people involved. I think this is really very important because all that NITheCS does is based upon collaboration, and that doesn't go without interaction. And although we are all COVID-proofed and zoomed out, a meeting in person is always a good plan. Yeah. Okay, sorry. Okay. My name is there. Yeah, but I guess most of you probably know me. Yeah. I just wanted, when you get involved with NITheCS and you invested lots of time to set it up and get people involved and so on and so forth, you learn very quickly that you have to act like an old LP that is stuck on a track, yeah, and keep repeating the same things, yeah? Because you want the message to go out there, yeah, and that's why I want just in 10 minutes briefly remind you of what all of this is about, yeah. So NITheCS, as you know, was originally is grown out of the NITEP, the National Institute of Theoretical Physics, yeah. But now we have a much wider scope, yeah. And what is really important to keep in mind is that we have in our constitution 4 pillars, yeah. Primary research, training, engagement, and getting involved in Africa promoting theoretical and computational sciences. Yeah? That is the pillar that we have neglected the most so far because we were mainly busy in making sure that it works in South Africa. Once we are settled here, we will push that agenda as well. Yeah? But as you know, we are no longer only theoretical physics. Yeah, we are also astrophysics and astronomy, which were already partially within NITEP before because the border is a little bit diffuse. Yeah, but most importantly, we have now mathematics, statistics, data science, quantitative biology, quantitative finance, and earth systems and climate change modeling. Yeah, so we are really essentially of theoretical and computational in the basic sciences, except chemistry is not explicitly mentioned there, yeah, for whatever reason of DSTI and NRF. But we have a research program on computational material science, which is partially chemistry. Chemistry at some stage is the interesting part of chemistry is physics. so we are a little bit flexible on that side. Yeah. And, when I started giving this talk, I like to do a little bit jokingly, call us an undisciplinary institute, yeah? Because, you have so many disciplines and you can't identify and promote just one, yeah? A better word, I think, is pan-disciplinary, yeah? And I will explain you why, yeah? The reason is that we really want to integrate the disciplines to address interesting challenges, yeah? And the priority should be to solve interesting problems. You want to understand the quantum universe, that's a very interesting problem, yeah? But you might also need help maybe from data scientists, from astrophysicists, yeah? From mathematicians, yeah? From maybe quantitative finance in that respect is not so relevant, but maybe just to get the funding yeah, could also be important. Yeah? So we really want to have the challenges at the center and pull in expertise from the discipline that we have access to. Yeah? So that is really important. Yeah? Why it is very important? The other aspect of pan-disciplinary science is that we really want to be inclusive. Yeah? I know my theoretical physicists. Yeah? They think they're the best. Yeah, and they are probably, but you're not allowed to say it. Yeah? You're not allowed to think it anymore, yeah? Because we should get everybody involved. So we really want to focus on problems. Yeah? and to encourage really collaboration without boundaries. Yeah? The only tool that we have to do that is to embrace open science, yeah? All aspects of open science, yeah? From traditionally open software and so on and so forth, but there are also other open access publication and so on and so forth. Yeah? But most importantly, a battle that we want to promote is that we need access to computational resources. Yeah? Grok 4 was developed with 200,000 high-end GPUs. Yeah? Do you know how many GPUs our CHPC has? 10, 100,000, 10,000? Guess? 30. 30. Yes. That's the reality. Yeah. The biggest high-performance computing center accessible to academics in South Africa has 30. Yeah, they're upgrading. I think they have a plan to upgrade shortly. Yeah, so maybe they might have 100. Yeah, but it's several orders of magnitude difference. Huh? So we have a problem. We definitely. The CHPC. I don't remember, but some standard NVIDIA something, yeah. But not the ones that Elon Musk has because they're much older. Yeah? Some of the middle GPU. Yeah? So open access is important. Yeah? Open codes, of course, part of open source and so on and so forth. But now in the age of large language models, open weights is also important, yeah? Because none of us would be able to train a Grok anything, yeah? Because we don't have unless we have lots of time, yeah? Years and years and years on 30 GPUs, yeah? Which doesn't sound like fun, yeah? So we need also to battle to fight for open weights, yeah? And luckily, we have this MOU with ICTP, and they have exactly the same goals. Yeah? So they also strongly promote open, these maybe more modern aspects of open source, of open science. Yeah? As you know, we are a consortium of all universities in the country and aims. Yeah. So last year, the first agreement was signed, and we are organized in 5 nodes. I think it comes here, yeah. And nodes have branches, so we are a little bit like a bank. Yeah, we need to find the equivalent of ATMs. Yeah? But so as you see, Gauteng is the node that has the most branches. Yeah, but that's because historically lots of universities are in Gauteng. Yeah, in the Western Cape, we also have a few. KwaZulu-Natal, but the Eastern Cape and Free State are put together in a node, and all the university sort of at the north are also put together in a node. So ideally, we should have as many nodes as provinces, yeah, because of the geography of the country. But those were the parameters of the STI, and maybe going forward, we can convince them to allow us to change a little bit the structure. Okay, here's just the same. You see the distribution of universities. Yeah? That's how it is. Yeah? I'm sorry. What is interesting is that at the moment we have probably more than 350. This was the statistic at the beginning of the year. Associates distributed across the various universities. You see that there's a bulk of usual suspect universities that have lots of associates, and a long tail of university where we have maybe just 1 or 2. Yeah, and that's where we need to put work. Yeah, we need that long tail to increase, because probably in the big universities and the research intensive university, we are probably close to saturation point. Yeah, I think. Sorry, on that note, which is very, very important, I deviate a little bit. In the past, everybody who wanted to become an associate sent us his CV, and then we shared it with people in the discipline. If they agree, we made them an associate. Yeah? That was a system that we don't follow anymore because it was just tedious. Yeah, it was just and prone to errors because then application got lost and so on and so forth. So now we have, at the moment, an open call until the end of July. for associates to nominate new associates. Yeah. So that is very, very important for the focus areas, yeah? Because you have in your focus area the same problem, yeah? That in this long tail, there are very few members of your focus area, yeah? So if you know of people, yeah, nominate them, yeah? Just go on the website, there is a Google form, nominate, attach the CV of the candidate, and then in August, we will put together a little panel, and one day we sort it out. Yeah? So that's what we will do going forward. Yeah? Once a year, we will have a call for new associates. Yeah? And it's up to you to identify worthy new associates. Yeah? In particular, in the long tail. Yeah? So this is, okay, the same plot in a different, of course, the largest number of associates is, of course, in Gauteng and in the Western Cape. Yeah, so there are provinces where we have two or three associates. Yeah? That's not so good. Yeah, we need to work on those and increase those numbers. Yeah. Just to show you again with the same data at the end of 2024, yeah, we will update it at the end of the year again. Yeah, you see, theoretical physics doesn't have the majority in the NITheCS parliament anymore. Yeah, NITheCS is a kind of a GNU. Yeah, no discipline has the majority. Yeah, yeah, theoretical physics is roughly maybe between a quarter and a third of the. Yeah, and what is nice is that, for instance, mathematics has apparently embraced NITheCS, yeah, as did the data scientists. Some disciplines like climate change modeling, yeah, they're small. Yeah, there are not so many climate change modelers in the country, yeah, so they won't. Yeah, but there are lots of biologists and bioinformaticians, yeah, that we still struggle a little bit to get involved. Yeah, but that's mainly because they have much more money than we do. But maybe now with the US not funding so much, they might be more open to collaborate with us. Okay, these are the 10 focus areas that we have. Yeah, yeah. Where are you? The DU, Decoding the Universe. Yeah, and yeah, and it might be interesting for you. Yeah. I need to treat all the focus areas at the same way. Yeah, so it's interesting to have a little bit of statistics. Yeah? So you see here's the number of focus areas in which a single university is involved. Yeah, so you see the usual suspect for Stellenbosch, UCT, WITS are involved in many focus areas. Yeah? None is involved in 10 so far, yeah, which is quite odd, but maybe it will change. Yeah? Yeah? Some university, again, usual suspect, yeah, Fortea, the Vaal University of Technology, Mpumalanga, they're not involved in anything. Yeah? And that is not good, yeah, because when I showed this to our first meeting of the steering committee, you can imagine what the complaints are. Yeah, those are exactly the universities that we need to help. Yeah? So please, if you identify colleagues in those universities, invite them to join the focus area. Yeah? So these are just the raw data. Yeah? This is also interesting. How many associates are involved in the various focus areas. Yeah? Here you see, mathematics, this is a fantastic job. They have almost 60 people involved, yeah, in the research program. Yeah? You guys are medium, not as bad as these guys. Yeah? These guys are the worst. Yeah? Yeah? These guys are also not doing very well. Yeah? So we need to work with these pillars and at least reach everyone above 20. Yeah, that will be my goal for next year. Yeah, to push every research area to have at least, and it shouldn't be difficult. I know there are people out there. Yeah, and each of you probably knows someone who knows someone who is at one of the university where we need to uplift the situation a little bit. Yeah? And I can't stress this enough because the STI and NRF, that's what I want to achieve. Yeah? The reason why we have NITheCS is because they were not happy with how the centers of excellence operated. Yeah? The center of excellence remained very localized. Yeah? it didn't fulfill the mandate of uplifting the whole. Yeah. That's why we have now this new strategy that everybody is involved from the beginning, yeah? But it's up to us to get people involved. Yeah? So don't underestimate that point, because that will affect seriously the funding that we get. Yeah? The other super important thing, yeah, that maybe is not so relevant, maybe for your focus area, but maybe for others, yeah, that both NRF and the STI doesn't want us to act like a funding agency. Yeah, so they really want the funding that they give us to be invested in the research programs to support collaborative efforts. Yeah? This is super important because, almost 2 months ago, I was a week in China at the University of Science and Technology of China in Hefei. Yeah, they have a quantum department, yeah, for science and technology, yeah, which is a campus off the main campus, yeah, where 1,000 people work on quantum science and technology. Yeah, how many of us are here? Yeah. There are orders of magnitude difference, yeah, in the number of people that they have focusing on.
Difference in funding, or is it magnitude?
Yeah, no,
right?
yes, that as well. But if we don't cluster and show them that we can also collaborate, they won't give us more funding to collaborate. Okay, so that's it. That's my little sermon on a Wednesday morning. Yeah. Do you have any questions?
Did you not say you had associates at all of these universities, or is the point that they are?
No.
They do not have associates. So I was confused.
No. We have associates at all universities, but not all of them are involved in the research programs. Yeah.
So that sorry.
Uh,
Oh, I just everyone.
No, there are people that thought it was a good idea to belong to NITheCS, but then they didn't make the effort for whatever reason, yeah, to join one of the research programs. Yeah, but now we need to counteract, and and the research programs we go and look for them, yeah, and see. There are probably many others, yeah. Every university has an applied maths department, yeah? So there will be someone that does something quantum somewhere, yeah? or something closely related. Yeah? So, and we need really to go out there and find them. Yeah? In the ideal world, every associate would have some role in a research program. Yeah? But we live in a first approximation of an ideal world, and unfortunately, it's not like that. Yeah?
There is no way to access any money if you're not part of the associate.
No. We have bursary for students, yeah, and that's the other battle that I'm trying to fight with NRF. At the moment, our bursary program is administered by NRF. The students apply on the NRF website, yeah, and then it's out of our hands, and it becomes a lottery, yeah, because at some stage NRF sends Rene an Excel sheet. It says these are students out of which you can pick your bursary holders, yeah, and there is zero correlation between our research programs and how the bursaries are awarded. Maybe a little bit by coincidence, yeah, but not by design. Yeah, and what we really would like to have is to go back to the NITEP system, which other programs in the national system also have, and allocate our bursaries like we deem fit. I like to say every research program get 5 PhD students, yeah, and then you choose your 5 PhD students, yeah? Or something like that. Yeah, ideally, of course, many more, but slowly we will get there. Yeah? So that's a battle that every steering committee will fight, yeah? And hopefully, eventually, we will get there. But not this year, because this year the call is already underway. So hopefully, maybe for next year, yeah, we will try to decouple from the NRF bursary system. Yeah? But at the moment, we award around 30, 40 bursaries between masters and PhD. Yeah? What I would like to do again, which NITEP didn't do, is start also bursaries for honor student. Yeah? NITEP at the beginning had bursaries for honor students. And then we stopped that program because you gave bursaries to students at honors level to do theoretical physics, and then they end up doing not theoretical physics but master. So it was not a good investment. Yeah. But now it doesn't really matter, because if they do honors in theoretical physics and end up doing the masters in mathematics, that's fine. They stay in the family. Yeah. So that's maybe it's also a good idea to, if funding permits, to reconsider supporting students also at honors level. At honors level, all we do is the internship program. Yeah. We at the moment we have here in Stellenbosch, we have 10 internship students. Yeah. And the idea is to help them in their honors project. Yeah. And that's why we do it in these holidays and not in the next one, because the next one is too late. Yeah. So we have 10 here. NMU has a big bunch, and there are a few scattered across the. At WITS, you also have a few. Yeah? Yeah. That's the only thing we do for honors students at the moment. Yeah? Any other questions?
Okay, thank you, Justin.
Yeah. No, then maybe, sorry, just some logistic things. This evening, we organized a little reception here. Yeah. At what time? 5:30. Yeah. When you finish here, it should be just outside here where the coffee break is. The bathrooms are at the end of the corridor where the main entrance is on the right. Yeah. There's one here, yeah, just around the corner. Yeah, that's true. Then in your documents, you should see the invitation for a dinner for tomorrow evening. Yeah, that we can walk there together after the 2 public lectures, because it's just a 5 minutes walk from where the public lectures will take place. Yeah, okay. And I think that's it. Yeah.
Okay. So
yeah. No, thank you very much. Yeah.
Okay, so Vishnu asked me to chair the rest of the talks. Sorry.
Yeah, I think I will see you, Vishnu. I will see you at lunchtime, because I need to go now.
That's fine.
So then that makes probably sense.
Yeah. Can I hand you the second microphone and then the speaker will just take over?
Sorry?
For the dinner?
Or just confirm your non-attendance. That will probably be easier. Sorry? Okay. Then we assume that everybody comes. So if you don't come, let me, Rene, or Mbali know. Yeah, and we'll make a plan. And I will see you at lunchtime. Sorry, I have other things to sort out now. Yeah. Thank you.
I'm trying to see who's connected. I'm just thinking for the online participants, okay? There's almost 20 people online. So I'm just wondering who I could ask you, Hank, if you don't mind, maybe just to keep a look, because at some point somebody was saying the internet connection, but that's stabilized now. If Hank can just maybe communicate to you.
Sure.
If there's any questions or
I can also connect and then I'll.
Okay, so I'm disconnecting now. And you guys are the all co-hosts, so if we want to make, you can offer them to make your host.
Should I say another host?
I think so, so that the connection is here.
Yeah.
But it's not, if you co-host, just to hold along in case there's any difference.
I'll ask them to do so.
Okay, so I'm disconnecting from there.
Have a nice one. See that. Thank you.
Thanks,
Thanks,
excellent, yeah. All right, well, so I haven't really had a chance to say hello to everyone. Good to see everyone. Thanks a lot for organizing this event. It's always wonderful to be in Stellenbosch and to see friends, always excellent. Now, I put together this talk largely based on the proposal that I sent in when this was all put together. But I don't think this quite reflects the message that I want to convey. The message that I really want to convey here is that there is this tool, collective field theory. Over the last couple of years, a lot of progress has been made to understand this construction. And I think there's a lot of applications that's possible there. I'm going to focus on one of these applications that I think is reasonably straightforward, but I suspect there are many other interesting ones that we could consider. So I took heed of Vishnu's instructions, and there's not going to be a lot of detail. I'm not going to discuss any past papers really. I'm going to give brief summary of the tools involved, and then to focus mostly on how this can be applied for future topics. All right. So the main setting is collective field theory. Now, for those of you that aren't familiar, what collective field theory is, it's an idea that's been around for quite some time. Goes back to work in the 1980s by Yavitsky and Sekita. If you're given some quantum field theory with a UN or ON gauge symmetry, you can define collective fields. The collective fields are basically the gauge invariants in this theory. So for example, if you have a vector theory that has a single index there that transforms under the gauge group, then the dot product between these vector fields, that is a gauge invariant. Or if you have matrices, for example, they have two indices that transform under the gauge transformations, you can put together trace operators. These are gauge invariants. Or in general, multi-trace operators, these are gauge invariants. What you're basically doing is you're reorganizing the field theory to no longer perform the path integral over your fields phi. Oh, all good?
Sorry.
Oh, that's perfect. You're no longer writing the path integral in terms of the fields phi, but you're writing it in terms of these collective fields, these gauge invariants. And there's a transformation that you can perform. There's an associated Jacobian. You get an updated action in terms of the collective fields, but it's essentially a repackaging of the theory. And two examples that are pretty well studied is the ON vector model in a very famous paper by Robert de Koch, Yavitsky, Jean and Rodriguez in 2011. And over the last couple of years, collaboration of Robert de Koch and a number of other co-authors, myself, Gary Kemp, Minkyu Kim, Pratik Roy, have been working on the free matrix model. So it's an extension of the vector model, and I think this is pretty well understood by now. There are certainly some open questions still, but a lot of the detail has been unpacked in terms of how this works. But there are just two key things to take away. As I said, I'm not going to go into it in a lot of detail, but just a couple of key things to know about this construction. The first is that the reason that there's a lot of excitement about this, even going back to the original work, is that the collective field theory description of these theories reorganizes the theory in such a way that your expansion parameter is no longer h bar, it's 1 over n.
I'm trying so hard to.
No worries, Isabel.
I promised I would look at the keep an eye on the chat.
Excellent. No worries. So it reorganizes the theory in such a way that you get a different expansion parameter. For those of you that are familiar with holographic theories, this should be very that should be a reasonably exciting replacement because the expansion parameter on the holographic side is usually 1 over n. N here is the rank of the gauge group in this case. That's the first point. So because of this, you would expect that if you take a general quantum field theory, you repackage it in terms of the collective fields, you will get a dual theory. It's a repackaging of the same theory, and there's a good chance that this is a gravitational dual theory. Is it always a gravitational dual theory? This is still something that's been investigated. Certainly for the vector model and the free matrix model, it's known that these are gravitational dual theories, and specifically these are higher spin theories. So as I say, whether it's generally the case is not known. That's a very interesting question, certainly. But the second point is that not only does it provide you with this reorganization of the theory, it's a constructive procedure. You give me your field theory of interest. There's a very explicit way to map from the original degrees of freedom to these collective degrees of freedom. And often in cases, you can use symmetry as a very good guideline to get the mapping exact. So certainly the repackaging of the theory is well known, and the repackaging of these into the gravitational coordinates and degrees of freedom is known for some examples at least. For the ON vector model and the free matrix model, this is very well known and very explicit. And again, I'm not going to sketch all the details, but let me just maybe put a sketch here. So this is for the ON vector model. This is basically, what you should think is that here on the boundary, this is where your bilocal degrees of freeze live. It's bilocal because you have phi dot phi. So there's two different coordinates to take care of. This is for equal light cone time phi's, so for light cone time fields. So they'll have one position. So you'll have a position and you take a Fourier transform of the x minus coordinates to get a p plus. And so on each point here on the boundary, you can think of a set of, or a bilocal pair, one at x1 and one at x2. So phi x1, phi x2 living. And the way this maps into the bulk is that from the center of the two coordinates of the fields phi, there is some disk in the bulk. Z here is the bulk coordinate. And this maps to a particular point in the bulk and some collection of fields in the bulk. That's determined by the specific fields that you considered with an angle theta. Theta is essentially packaging the different higher spin fields in the bulk, and you can isolate a particular one by performing a particular integral over theta in this case. But it's an extremely explicit mapping. The key thing to take away is that if you give me a particular bilocal, it maps to a particular point in the bulk and some collection of fields living at that point in the bulk. Right. Now, this is all great, and there are many interesting questions still relating to this construction. What are the implications, or how can you find signatures of quantum gravity in these QFTs? How do they come about? Things like entanglement wedge reconstruction, holography of information, diffeomorphism invariance. How do they show up in the bilocal description? These are very interesting questions that certainly Robert and friends are still thinking about. But I want to focus on something a little bit different for today, which I think is a different way that one could also apply these methods. One of them is in terms of complexity. I'll get to how exactly I'm thinking about it. But the point is that we have this very explicit mapping from the boundary to the bulk. And we can use this to answer specific questions that have been floating around, especially in the complexity literature and probably in other fields as well. So what exactly is complexity? I'll tie this back to a holographic description just now, but it's essentially a reasonably simple question. So you're basically trying to quantify how difficult it is to synthesize a target state from some reference state with some set of unitary operations. So I have a target state psi of t. I have an origin, this shouldn't be phi of t, that should be psi of r. But anyway, this is your reference state, that is your target state. And there's some sequence of unitary operations that take you from the reference state to the target state. So you're given some set of allowed gates, some set of allowed unitary operations, and I act on my reference state in order to generate the target state. Here I've taken a discrete example. You've got 3 gates, U1, U2, and U3. Some sequence of them takes you to the target state, and I can assign a cost associated with this, a computational cost associated with that operation. Say each unitary here has a cost of 1, then you'd say that target state has a cost or a complexity of 6. So this is sort of a toy example, but these unitaries can be many different things. They can be a set of continuously parameterized unitary operations. This gives rise to a so-called Nielsen complexity. This could be the time evolution of a particular Hamiltonian and superpositions. This gives rise to Kirchhoff complexity. And so on. But the point is that there's some choice of allowed operations. You give me a particular cost function, this will define complexity. Now, there's a great deal of arbitrariness in this. This is probably why it makes a lot of people uneasy. What is the physical motivation for choosing a particular set of unitaries or a particular set of reference states and target states, or a particular cost function? Some of these have some physical motivation, but it's not entirely clear. But that's a different question. For now, I just want to point out that there are questions relating to complexity in a holographic context, several conjectures made, and you can test these very explicitly using collective field theory, or at least that's the proposal. So you may ask that, say you're given some cost function and you're given some set of unitaries, what is the holographic dual of complexity? So computational cost. Now, this is a question that's been asked before. And the eternal black hole is an example that has been discussed in much of this. So, for example, there's a couple of papers that I'm sure some of you may be familiar with. From a 2014 paper, there was a conjecture put forward by Stanford and Susskind that complexity should be dual to volume. The volume here is the volume of a wormhole connecting the two horizons of the eternal black hole. Then there was a paper in 2016, complexity equals action. And then a couple of years ago, there was a rather tongue-in-cheek one, complexity equals anything. That was put out. But essentially what it boils down to is depending on how exactly you define complexity, depending on then there can be some dual quantity, some family of dual quantities that could potentially be obtained. Yes, 5 minutes. Yeah, I'm pretty much done. I just maybe want to sketch very loosely how through collective field theory we can actually make these answers and questions very, very precise. That's what I suspect. So given a choice of unitary operations and cost function, what the complexity is, it's essentially synthesizing a target state from some sequence of unitary operations. So you give me some gauge invariant, some reference gauge invariant. I can act with this sequence of unitary operations in order to generate a target gauge invariant in this case. And this quantifies some flow from a bilocal or multilocal field to another multilocal through the sequence of unitary operations. The point is that in the collective field theory description, at least for the Owen vector model and the matrix model, it's known exactly what the dual quantities are. It's a very precise mapping. So for every QFT operator, these gauge invariants, there's a corresponding point in the bulk and a corresponding set of bulk fields. So as you're synthesizing this target state from the reference state for a sequence of unitary operations, this will correspond to a sequence of some flow in the bulk from one point in the bulk to a new point, and some set of fields at that point to some set of fields at the new point. So you can have very good control over what the synthesis process is from reference to target state in the bulk through the collective field theory mapping. So since you can track this very precisely, it should be possible to make precise statements about various choices of complexity measures. So what is Krylov complexity dual? What is Nielsen complexity dual to in the bulk? Making use of this very precise mapping in a holographic context. This, as I say, this is one possible proposal. So this is one thing that you could foreseeably do with the mapping. There may be others. Happy to hear any ideas or discuss any ideas, or if you want more detail on this, more than happy to chat about that as well. That's pretty much all that I have. Thank you.
Thank you. Are there any questions?
Sure.
So you showed an equation where a reference state, so one state is going to another state via a set of unitary transformations.
That's right. Yeah.
So this is the case for quantum mechanics, or
So
generalize this to a quantum field theory system?
you can absolutely, yeah. So there are generalizations of this to QFT. So here I've written really the simplest toy example, which is a quantum mechanical example. That's some set of unitaries taking you from a reference state to a target state, but there are generalizations to QFT as well. Yeah.
Now, so could you give an example where you give the starting point and end point, so that we can understand, the physical interpretation? Are we tracking some kind of observable or?
Yeah, so I think probably the most physical thing I can think of is, think of your unitary operations being time evolution. So you give me some Hamiltonian and superposition. So recently we demonstrated that you can use this to think of a notion called Krylov complexity. You can think of Krylov complexity in a very precise way in terms of these two operations. So, and say that you want to ask questions about that Hamiltonian, whether it's chaotic or integrable, for example. So you'll have some sequence of unitary operations that take you from your initial point to some final point. And depending on, so this will define some flow in the Hilbert space from reference state to target state. And then you can compute the computational cost with those two operations to synthesize the target state. And does signatures of chaos or integrability show up in that? So that's one of the questions that you may have. Again, various conjectures out there, nothing rigorously proven, but there are some features of a chaotic system that show up in that case. Yeah, not sure if that answers it exactly, Anish, but yes.
Thank you. Sort of start with this program or this idea. Would you start with or by looking at vector models? And then maybe moving on to sort of the matrix models. And also, what would be maybe more interesting? Would matrix models be more interesting?
Yeah, it's so I was actually thinking of possibly starting with the matrix model. To be honest, I think simply because I don't know. I suppose it's just something that I've worked on quite recently, so I'm more familiar with it. Not sure whether the vector model might be easier to start with, but. I was thinking of starting with the matrix model in this. Unfortunately, I haven't actually started working on this. It's still just a set of loose ideas, but I am hoping to start on something like this in the near future. Yeah. Excellent.
Show you quite when it's ready.
Just make sure it's software or not.
Oh, of course, yep.
So I'll just introduce you. I'm David Johnny from NITheCS.
Okay, thank you. Morning, everyone. Yes, my name is David Swani. I think I'm one of the NITheCS Associates, but mainly on the quantum material computing. So now I will be sharing with you the application of quantum chemistry in sense of improving the mechanical properties of the material and in which one could synthesize or characterize the material using quantum chemistry. So I will mainly focus on few topics: the quantum research and properties, the challenges and maybe the suggestion that we are encountering, the application of these quantum materials, and the emerging quantum chemistry in the era of quantum computing, direction and the collaboration in which the two could be work together, and then what are the new theories that could determine the new quantum chemistry. So of course, the age of quantum materials started long before, where they assign it as the big black elephant together with a blind person or individual. So in which you will see that this is a big things to do. One is the method, the material, the mechanism, and also the manufacturing. How could we integrate all these things together to come up with a solidus thing? And of which, when we look at the brief of material research, the quantum material are class of the material whose properties are primarily determined by quantum mechanics, and then rather than the classic physics itself, and are characterized by the collective and often non-initiative state of the electrons. And then it started long before in maybe in the 90s, where we'll talk about the quantum Hall, and then where the main part was the Curie temperature, in which we are looking at the superconductivity. And then in 90s, and then it falls to the nanotechnology or nanomaterials, in which one of those is the study of nanoparticles. And then in the presence, of course, together with the future, already now we are talking about the devices in quantum that use quantum materials. And then also in the future looks like a quantum computing, in which we can use these quantum materials to perform some quantum computing, of course. And then one of those important part there is quantum simulators, of course. So these properties could be classified in maybe three, where in which the quantum confinement plays an important part, and the strong electron correlation, in which if you train these two material, how the electrons are correlated within each other and can have a material strength or enhance the material strength. And then, of course, in this sense, maybe we are looking at increasing the band gap with a decrease in size. So we don't have a situation whereby the simulation is too complex or is big, so that it could not even be computed within the given time scale. And then, of course, the strong correlation look at the fact that the superconductivity. So we are trying to find out the material that could be performed at the superconductivity. And then the topology and the symmetry, of course, is looking at the surface states, in which where we can study the surface of the states. The quantum material research vested between the density functional theory. This high throughput calculation method, such as density functional theory, has accelerated the discovery of quantum materials, in which it predicts the novel materials. This principal method is used to solve electronic structures and energy of the material based on the Schrödinger equation or approximation, in which the exact theory, the practice of the accuracy depends on the approximations and also the property of the material. So the calculated, the ground state energy, which depends on the density of the system. So if you look at our right-hand side, those are the ladders of Jacob's ladders, where in which the lowest state is the localized density approximation. That is the default accuracy of the simulation. And then when you go up, we get the GGA, which is generalized gradient approximation. And then when you go to the further up, that's where we talk about the high throughput. Therefore, the only problem or the complexity is that the more you go up the scale of the ladder, that's where your simulation becomes more complex, but most importantly, accurate. That's where, as the quantum simulation now, we wanted to go to the last ladder, but within the resource of computational, we are limited to go to the last ladder. So we are hoping to say, if you use the quantum computing, we could also be able to get our simulation to the highest accuracy. So the localized density approximation is whereby we only look at the dot point, of which it doesn't give us the broader perspective of the accuracy of the simulation. And then the generalized one is where you look at the region. But now we wanted to go as the what do you call the correlation, where in which our simulation become more accurate as we go to the exact correlation, and of which this has been done more, but only looking at the localized and also the generalized gradient approximations. So in high performance computing, of course, the application is vary across the sphere, and of which the high performance computing shows in government labs. The government labs in this state now, they are more relying on computational and modeling and simulation. So from the electronic point of view, we have to simulate from electrons up until the microscale, in which that you can start from the microscale going down, or you can have a point where you start from the bottom going up. But the system itself, it should be integrated in such a sense that we can simulate from all levels of the scale. But now, what does this quantum innovation can bring? If we are able to do it from the classical computing, then it means that with quantum computing, we will be able to accelerate from where we are to get the more accuracy in terms of an application. And you could see that the quantum material devices, of course, looking at the superconductivity, which that's where we wanted to focus our future focus on, in terms of designing a material that are superconductive, and especially in two-dimensional materials that have been not being studied so far in terms of classical computing. But now the application of these quantum materials cut across every sphere of physics. It could be in photonics, electronics, and also on the spinotronics. However, the most important part now is, can we do this quantum computing from the microscopic application and also from a micro application? If we could do the same thing that the quantum classical simulation could done, it means that with quantum computing, we could be able to improve our discovery of a material using quantum computing. And of course, the quantum technology innovation and the materials, we are looking at the two-dimensional materials, of course, at this point, where in which we know if we combine the two sheets of graphite, it will give us the strongest correlation. But however, because in quantum now, in classical simulation, when you have two sheets, we have a lot of lattice mismatch. Of course, that itself makes the simulation more computationally intensive. So we thought maybe of using the quantum computing, we could be also able to increase the strong correlation. And of course, the physical properties that we are looking at there is the most important part is the superconductivity. This quantum application research and the challenges and the solution, we could see that in this quantum, the challenges at this point is the compatibility, and then also the computational, the material and the mechanism prediction, in which that we need to reduce the experimental load. So we don't have to go in the lab and run the experiment that we know simulation work. It won't succeed. So we wanted to use this quantum application in such a sense that we could be able to reduce the experimental load. Of course, in this instance, the synthesis of the material, we are looking at the quality of the material in which it could be synthesized. So if this quantum computing could be able to give us the accuracy of how we can synthesize this material for scalability, we could be using this part. And of course, the short term and the long term in this solution, of course, we are looking at the existing quantum computers to solve the new quantum materials that are, of course, in place. But most important part now is here to use the machine learning, in which that we know that if we are able to do the machine learning application, that's where we could be able to discover new material through machine learning application. But now, the quantum chemistry versus the era of computing. I've talked about the limitation in which the classical computing we are experiencing when we do the material design and then the discovery. So we have thought maybe coming with the quantum method, one of the methods could be able to get increase the accuracy and also to at least increase where the classical computing is in. So what are the emerging research direction and collaboration? One of the fields that quantum material is heavily involved in new research, pushing the boundary of engineering and physics, is if you are looking on the non-Hamiltonian quantum material, the complexity of engine values. Of course, I've mentioned that we have to be beyond the linear models. We are more on the linear model, but now, if we go through beyond a linear model, that's where we'll be able to explore the system with a gain and a loss, leading to phenomena like exceptional points and asymmetric transport. Of course, I've mentioned that the machine learning aside for material discovery, it has been advanced in discovering and characterizing the quantum material, identifying the pattern in which you can predict the property of the quantum synthesis. Of course, the high throughput screening of this candidate quantum sensing and computing design the defect of engineering system like a deepen. So there is an advance in this case. We can reference the quantum defects on the utilization of AI in this sense to potential quantum defects. So now, if we are looking at the flat bands and also the more super lattices, wherein which the increase in electron correlation allowing us to have a novel phenomena such as superconductivity and correlation of insulating states. But what do we want to gain from this to enhance the correlation in which that even the tiny Coulombic repulsion become dominant at some? at some point. As I've mentioned, that these are more in two-dimension material, in which if you twist the sheet in any direction, that's where we lose the lattice mismatch. And of course, if we apply the flat bend, that way we can improve our lattice mismatch. And then the focus, of course, is in using the machine learning. Now we know that the classical machine learning it has been accelerated so far, but now we have to go and refocus on the quantum machine learning, in which we will be able to characterize so many material and also improve the application of material design and discovery. I think I can stop so far. And thanks.
Thank you very much, David. Are there any questions?
Can you talk a little bit more about the finite system type effects on the quantum mechanics and quantum chemistry?
Sorry?
So you've mentioned on some early slide that you're interested in understanding what happens when your system becomes small.
Yes.
If you talk a little bit more about that, please.
Now we wanted to, if we look at the simulation system point of view, if now we wanted to simulate a material on maybe a stack of layers in which we determine the insulator, semiconductor, insulator, and a semiconductor. But the problem is like now when the system, when we grow our sheet of layers, it's becoming more complex. We wanted a sense that whereby now we know that the system becomes small, but also increasing the accuracy of the material, like increasing the band gap of the material at the smallest scale.
Your previous slide, what exactly are you doing?
No. I said maybe on non-Hamiltonian model, that's where we could be able to reduce the bigger lattice mismatch that we have experienced when we twist the sheet of a graphite.
How much do you have?
Yeah. So following up on Pallav's question, on one slide you mentioned about non-Hermitian, I think.
Yes, that's
And
right.
you mentioned something called exceptional point. Could you tell us what that means?
Slide.
Exceptional. Yeah, right there on the right hand side, the same slide. Exceptional points. What? How do you define an exceptional point in the system?
Okay, exactly. That's where we are saying when we are looking at the localized density approximation, like a LDA, that's one point that we are looking. But we wanted to get, if we have 5 points in this, it's much sense that all these points can be connected to make an exceptional point. So we get the average of all these points.
So you would say points, are they points on the lattice?
Points on the lattices.
Okay, thank you.
Thank you. There was one question from online. Do you have an example of a material that you've got with quantum machine learning? Quantum machine learning, specifically to
No, I think in quantum machine learning so far we haven't branched much on that material.
Oh, so
That's the future focus. Yes.
thank you very much. I will continue to discuss it later, but let's see the next, I think is called those.
Okay, back.
1, 2.
Teacher American and
One.
okay.
And that's the three. I do need Yes.
Can I start?
I just did, it's not, okay, so it's all about the get started. Welcome back from the tea break. We have 3 talks remaining in the session. The first is about Southerners. Thank you. Sorry.
Thank you, thank you. Thank you, thank you, thank you. Good morning, everyone. Today I'm going to discuss a possible direction to the quantum mechanical probe of gravitational waves. And this is actually I have developed recently, and I will discuss some future aspect regarding this topic. Okay. So it is quite well known that the direction of gravitational waves, one of the most successful prediction of Einstein's general theory of relativity. And hope is raised that this will be the most useful laboratory to test the quantum aspect of gravity in terms of the gravitational waves. And the point is that all of you are familiar that the detection of gravitational wave based on the frequency range, actually first, the ground-based detection is based on the range of frequency within the hertz to kilohertz within this LIGO and Virgo collaboration. And there are other possible detections which is based on the space-based detection, which is of course the promising way for the low frequency modes of the gravitational wave. But the point is that the detection of the low frequency gravitational waves is one of the most challenged in terms of the ground-based experiment. The important point is that there are indirect evidence of the low frequency gravitational wave within the nanohertz band is recently confirmed by the pulsar time array approach. But the point is that our plan is, can we provide an alternative way or can provide some quantum mechanical way to probe the low frequency modes of the gravitational waves? And the reason is, the reason of this, the quantum mechanical probe of the gravitational waves, not only the detection of the gravitational waves, rather to study what would be the quantum response of the gravitational wave on a quantum system. So, why quantum approach is useful? Because it is really interesting that when we observe the gravitational wave in the LIGO experiment, the gravitational strain parameter is of the order of 10 to the power minus 21, and which provide the deviation for the arm length, which is of the order of 10 to the power minus 18 is a kilometer range. Now the point is that since LIGO has actually used the macroscopic mirror, and the corresponding the 0-point fluctuation of this macroscopic mirror is really smaller than this deviation induced by the gravitational waves. And since it is a macroscopic mirror, it's quickly decoherent, and therefore any quantum nature of this system will not be useful to study the gravitational wave detection for the case of the LIGO-like system. However, recently in 2022, there's some paper which actually provides some alternative way to view this problem in terms of the mesoscopic system. And this mesoscopic system, they introduce some mesoscopic mirror, which is basically the oscillator. So this is basically the movable mirror, and which is basically within the range of mass to the 10 to the power minus 12 to 10 to the power minus kilogram. And the corresponding this range, the 0-point fluctuation is 10 to the power minus 17 meter. So the hope is raised that is it be really a comparable to the gravitational wave induced shift to the arm. And so this is the point, this is the key point, is that there is some possibility that the gravitational wave, if we detect in terms of the mesoscopic mirrors, then the quantum nature of this mesoscopic system will be provide a most important role to detection of these gravitational waves. So this is the important point, and the point is that this mesoscopic system will still stay the coherence in presence of this environmental coupling, this rather than the macroscopic system. So let me provide some mathematical backbone to study this system. It is quite well known that to study any gravitational effect on a system, the most useful way to study this is using this geodesic deviation equation instead of the geodesic equation, because we know that the principle of equivalence tells us that gravitational effect can be absorbed apparently using this local inertial frame. So therefore, if we consider two time-like geodesic for a free-falling object, and if we study the geodesic deviation in presence of the background gravitational effect in terms of which is restored in terms of the Riemann tensor, and therefore, if you consider this is my starting point, this is the basic dynamical equation which actually encodes the information of the underlying gravitation effect. And if we use the linearized approximation to study the gravitational wave effect, one can immediately observe that linearization effect can be reduced gauge symmetry, and if you want to understand the physical degrees of freedom of these gauge degrees of freedom, you need to impose some the gauge condition, which is quite important gauge condition, and it is known as the transverse stressless gauge condition. And using that gauge condition to isolate the physical degrees of freedom of the linearized gravitational fields, and using this slow moving motion or the non-relativistic approximation, this geodesic deviation equation boils down to this particular form. And this form actually indicating that this is nothing but the Newtonian equation of motion. And the right hand side indicate this is just a tidal force. So this force actually originated from the gravitational perturbation. Now the point is that we can interpret, okay, this is my dynamical equation, and this equation encodes the information of gravitational effect in terms of this forcing term at the TT gauge, because TT gauge provides the physical degrees of freedom of this gravitational perturbation. Now if you consider the system also influenced by some other mechanical force, then we can just simply add the additional force term, which is the external force, which is not a geometric term. So therefore, we can start by considering this equation, this my dynamical equation, which provides the relative motion of a particle or a test particle with respect to some reference point. Now one can develop this equation of motion by considering this Hamiltonian, and in fact if you study the Hamiltonian equation of motion, I mean if you just rewriting in terms of the second order equation, you will arrive at this same equation. So therefore we can say that okay, the dynamical system which encode the information of gravitational perturbation and influence of the external field can be incorporated in terms of this Hamiltonian. So this is the master Hamiltonian.
You said that's the equation of motion for the detector.
Yes, yes.
That's the equation of motion that meant to be, well, the Hamiltonian for the whole detector, or for
no, this is the
equation.
So this is the equation of motion for a test particle with respect to a reference point, which is basically massive. So therefore, this is the equation of motion for the test particle, which is behaved as a point particle, our detector.
So okay, the point particle is
yes,
the detector.
Yes.
Okay.
And which which influenced by the gravitational perturbation as well as external fields. Now the important catch is that we can yes. So we can consider this is my model Hamiltonian for a point particle. And now let me consider the most useful setup. Since we have already considered the system can be modeled in terms of the mesoscopic regime, and then we can just consider the gravitational parameter, gravitational wave amplitude in terms of the linearly polarized gravitational wave is basically given by this following form. And if I consider the external influence is basically due to the external radiation field. So if you have the mesoscopic mirror influenced by this gravitational perturbation, and if we have also if we invite the external radiational field, so radiational pressure provides the additional force term. So therefore, we consider the gravitational strain by using this parameter. external perturbation, external radiational pressure is basically given by this F radiation, and also consider this particle trap within the harmonic modulation, which is externally time dependent. So therefore, we consider this is the following Hamiltonian, and we consider or we promoted this Hamiltonian at the level of operator valued object, because we consider our system is basically starting at the level of mesoscopic region, whose mass is basically of the order of 10 to the power minus 9. Now, the important point, look at this Hamiltonian. This is basically the harmonic oscillator, but it influenced by this squeezing term and also has some linear term. The interesting point is that this Hamiltonian is a beautiful properties. This Hamiltonian, let me call this is my detector Hamiltonian, and this detector Hamiltonian can be rewritten in terms of this unitary transformation, which is a successive two unitary transformation. And this is the sandwiching Hamiltonian, which is basically a harmonic oscillator, but a displaced harmonic oscillator. This displacement arising from this radiation pressure. The important point is this is the time dependent unitary transformation, and this is the expression, explicit expression of this successive unitary transformation. Since we are interested to study the gravitational wave, in particular the low frequency modes of the gravitational waves, and this low frequency mode of the gravitational wave provide the natural concept of adiabaticity. Because if frequency is small, the time period is very, very large, so system evolve very slowly with respect to this the gravitational perturbation. So therefore, this is the system can now one can start the evolution of the system with respect to this adiabatic transformation. So now, under the adiabatic evolution, one can immediately recognize that the system gather some phase, which is basically the usual dynamical phase, and also there are possibility that the system also gather additional phase, which is basically the geometric phase, actually developed by 1994 by Michael Berry. And now the dynamical phase is trivial phase, but the geometrical phase is basically given by this following form. This is the integral of one form, and now if we calculate carefully this integral, one can immediately rewrite this integral in this particular contour integral over the parameter space. So one can rewrite this time integral in terms of the closed contour integral in the parameter space, and this parameter basically defined by this gravitational wave amplitude and external parameters of the harmonic oscillator field. Now one can immediately recognize that the geometrical phase is basically composed two terms. One is the usual Berry, which is given by this expression. Another is the interesting part, which is look like Aharonov bomb-like phase. And it is really interesting because it goes 1 by h bar. So this clearly suggests that this phase has no classical analog, but this phase has classical analog, which is called the Hanning angle. Now the important point is that can you detect this phase? The answer is yes, there are a possible way of detection, which is called the Ramsey interferometric detection. And this interferometric detection is basically proposed the following step, which basically let me consider the following state, which is the state of the detector, which is basically the state of the mesoscopic mirror, and this is the state for the radiation field. Now if we use some radiation pulse, so therefore one can produce the final state. This looks like a following form, and this final state is the entangled state with the mirror and the radiational field. Radiation field, which is basically the vacuum state of the electromagnetic radiation, and the single photon state. Now if you project out on the vacuum state, you will get some additional phase shift, which is cos delta phi. Now ask the following question, what would be the nature of this delta phi? So therefore, this is the intuitive picture. This intuitive picture tells us that the mesoscopic mirror is basically a mirror as just a swing hanging from the tree, and the photon basically a person which is basically a seat in this swing. Now if this whole system influenced by wind is basically the gravitational waves. Now ask the question that how this boy will feel this, how did the ride is feel. So therefore the question is arise that how this phase occur in terms of this dynamical and Aharonov bomb-like phase. And for a particular case, I have calculated this phase basically based on two parts. One is a dynamical part, which is of the order of 10 to the power minus 20 radian. But the Aharonov bomb phase is 10 to the power minus 7. So this clearly suggests that this Aharonov bomb-like phase more dominating over the dynamical phase, and it is purely quantum response of the gravitational waves. So therefore, the key result is that we can provide a novel approach or to detect the low frequency mode of gravitational wave, which unify the Berry phase and Aharonov bomb-like phase. Why I'm calling Aharonov bomb-like? Because we have not say usual Aharonov bomb-like situation. It just look alike. Now we can detect this kind of phase using this Ramsey type protocol. And the point is that this Aharonov bomb-like phase is more dominating over this dynamical phase, so therefore it is easy to detect if it is possible. And this provides the quantum response of the gravitational wave. Now the important point is that this geometric phase basically, but the important point is that in usual Aharonov bomb-like phase is a topological phase. But here it is not a topological phase because it depends on the trajectory in the parameter space, or depend on the geometry of the circuit in the parameter space. So it is not a topology, it is a geometrical phase. But the point is that how this phase influenced by the external thermal effect, because thermal temperature effect can provide the additional noise. On the other side, whether this phase can be modified if we consider the quantum modes of the gravitational wave, say graviton. Because recently there are some one of the paper which basically published in last year, which provide a tool to detect the single graviton to confirm the quantum nature of gravitational waves. And the one of the paper by the Wilczek, who actually studied the similar situation, not in terms of phase, in terms of noise, which is basically the quantum mechanics of gravitational waves. So this is my conclusion.
Generally, the gravitational wave that is emitted by the
Merging of two. Yes.
How potent are those waves? Like the waves that comes from the stars, etc. Very incoherent.
So there are different stage. One is called the ring down phase, and other than this, after the ring down phase, when we detect, it is basically we are considering a very simple gravitational waves, avoiding the any quasi-normal modes effect. It is basically a trivial form of the gravitational wave, which is a plain polarized gravitational wave. It's true that it may be, you can consider most general form of the gravitational wave, and which is basically a true, which can modify the ultimate result of this wave.
But I'm saying that what do we see in nature?
Yes.
Just being polarized.
No. As I've said, that there are several stages. When gravitational wave is formed, then it's a ring down phase, and when gravitational wave propagate, if we consider the gravitational wave propagate, if we consider the gravitational wave around the source, then this is not no longer the plane polarized wave. But if you study the effect of gravitational wave far away from the source, the asymptotic limit, then it looks like a very simple plane polarized wave. For the simplicity, but it is one of the way to detect the gravitational wave near the vicinity of the source, which is basically the part of the black hole perturbation technique.
Sorry, what's the frequency of the phase mechanism?
Yes, I have already. Yes. I have estimated using. I have estimated using the gravitational wave frequency 10 to the minus 2 Hz, which is less than normal LIGO frequencies range. So it is basically the range of the LISA. Yes. But my detection is the interferometric way instead of the LISA is a space-based and it is a displacement-based approach.
So that just to get the basic idea. So the idea is you have this sort of mesoscopic mirror, and then you would use interferometry to precisely detect the displacement of this mesoscopic mirror, which is interacting with your gravitational wave.
Yes.
different from.
Yes, yes. But the key point is that the mesoscopic mirror, the phase shift
Yeah,
encodes the two type of phase. One is the system dynamical phase, which is usual, it cannot be avoided. Another is additional term, which has no classical analog. This is the interesting because dynamical phase, Bailey phase, or can have some classical counterpart. But if you see this expression, this is looks like iron or bomb-like phase, which is basically flux. One goes as 1 by h1. So you can't take classical limit because the classical limit is ill-defined here. And my point is that this phase will more dominating over and above the dynamical phase up for a specific range of
the
frequency.
mass in that equation, that's the mass of your whole mesoscopic system, which you need to be.
Yes, this is
in a coherent
updated.
state, otherwise it's not going to.
Say again, please.
You need the whole mesoscopic mirror
Mhm.
to be in some sort of coherent state.
Yes,
Otherwise,
yes.
it's gonna
No,
respond
no. Of course.
In no way. I mean,
Of course.
it's how technologically feasible it is. I mean, you say it's small, 10 to the whatever kilograms, but that's still a huge number of particles.
Yes, of
I
course,
mean,
of course.
that's kind of-
Basically, this there are some
That's
reference.
technologically feasible. I mean, what's kind of the biggest kind of coherent state? you can make?
Actually, the mirror state actually modeled by the coherent state.
No, I mean, it's like a practical. I'm not an experimentalist. But I'm saying, you know, an experimentalist. I say you need this thing which is 10 to the minus 12 kilograms. That's still a lot of particles.
Yes.
Like,
Of course.
what is the biggest
But
kind of thing we can build?
but
Which is
you
still
can
coherent?
think that it is an extended object because it is a composite object. But when gravitational wave interact with it, only the center of the essential dynamics is corresponding to the center of mass of this system. So we are only focused on the center of mass of the
Yeah, but all
system.
those particles, like if all those particles are not in phase or not coherent, any effect is going to be just washed out because everything's in like a different phase. I'm saying, what I'm saying is, okay, like the biggest kind of coherent systems I know about are like Bose-Einstein.
Separate. I read about it a few
Yeah.
years back. Roughly, this is like several million times more than something.
Okay,
Something of
But
that.
actually, I'm going to interrupt the
Okay.
conversation, just because we have quite a bit of time now
Yeah.
to do the discussions.
yes. go
Sorry
on.
about that.
Thank you,
Let's-
thank you.
Next, okay, now, thank you very much. I will pass the mic to questions. Okay, so what's the thematics? Because that's what I'm getting you.
Okay, what's the sense? I'm not the person who's trying to.
Yes. you're not going to-
No, sorry.
Here we go. Okay.
Oh.
I'm not sure how to remove those, but hopefully it's okay. So mute problems. Should I?
Sorry.
No, see?
I thought I already introduced you.
Oh, sorry. Maybe you did.
What's up here? So go ahead. I'll give you 5 minutes.
Okay, thank you. Okay, thanks. And yeah, so today, I guess I tried to understand a little bit the assignment of being more future-oriented, but I will today talk a little bit about what I'm currently doing and hopefully try to link it with some future ideas. So what I'm currently mostly working on is this topic called integrability in planar gauge theory. Now, I understand that not everybody here maybe is necessarily working in high energy physics, but we can. I will definitely take that focus, and we can also, in the afternoon or whoever has any questions about the details of this, I'll be very happy to explain a bit more. So I want to introduce gauge theory in this quick presentation. So I'll talk a little bit about my recent and current work in this topic, and then some future work in this topic, and then some other future directions not directly related to integrability. And then I will just spend a few moments on kind of the bigger picture. So, and there I will kind of put on my string theory hat and sort of talk about, how what I'm doing here is connected to what I eventually would like to do, given infinite time and, infinite energy, money, students, yeah. And mathematical kind of prowess and whatever. Yeah. Anyway, so let's start from the kind of basics in this topic, which is okay. So let's start with a gauge theory, and the gauge theory I'm going to start with is a supersymmetric one. It's a four-dimensional gauge theory, similar to QCD, but just much more symmetric and without quarks. But it has 3 chiral superfields, which are adjoint fields. So these are big matrices in the planar limit. And one aspect which is important is the interactions between these fields are given by this object here called the superpotential, which is kind of a symmetric thing. And okay, if you analyze it a little bit, you'll see that this is an SU3 symmetric object. So there's an SU3 symmetry here. And actually, that's part of a much bigger SU4 symmetry that this theory has. And that SU4 is kind of related to this n equals 4 here. Now, the idea about these spin chains, and this is actually kind of an important slide, so then I'm going to go into technicalities, but the main idea is that in a gauge theory, we are interested in finding out what is the, finding all the operators in the theory. And in a gauge theory, these have to be essentially traces, because these are matrices, so you have to take a trace to get something that is invariant, that is invariant, and then, well, oh, okay. I think it doesn't show on the screen. It doesn't show on the screen. And then on the other side of this kind of correspondence, you can map these operators to spin chains. So this is like a one-dimensional object. If you think of the x and the y as up and down spins of a quantum mechanical spin chain. And it turns out that if you calculate in the superconformal field theory one of the generators of the symmetries of the problem, which is the dilatation operator, it precisely maps to a Hamiltonian acting on the spin chain. So you can make a link between a four-dimensional theory and the spectrum of this, which is all the gauge invariant operators, and diagonalizing a spin chain. Now, the spin chain is supposed to be cyclic here, or periodic, but you could also do it for open cases, as I will discuss. And luckily, for this n equals 4 theory, the Hamiltonian is that of the Heisenberg spin chain. So introduced by Heisenberg back in the 1930s, and famously also solved by Bethe in terms of his Bethe ansatz. And it is very simple and in particular integrable Hamiltonian, which means that you can diagonalize this Hamiltonian for any length. So this is a very complicated mixing problem when you try to calculate this spectrum of these operators, but because it's integrable, you can actually solve it quite straightforwardly. So let me just spend a few moments on integrable systems, because that's where this integrability came from. Now, integrable systems come in two types. There's the classical ones. So you can start with the Kepler problem and mechanical tops. Then you can go to one-dimensional problems like KdV and nonlinear Schrödinger and Sine-Gordon. These are 1 + 1 dimensional. Field theories, you can go to Kp, which is 2 + 1. You can go to self-dual Yang-Mills equations, which are 4-dimensional, and supposedly give you all these other integrable limits as dimensional reductions. That's one of the kind of fascinating things that came out of the study of these classical integrable systems. And at the same time, you also have quantum integrable systems. So spin chains that I already mentioned, vertex models, phase models, and so on. So statistical systems that have some kind of integrability. And these are, what do we mean by integrable systems? I mean, they have some properties like, the fact that they're exactly solvable. There are, many additional conserved charges compared to what you'd normally expect, like, momentum and energy and so on. So you have to have many more charges, and they have very beautiful mathematical aspects behind them. So, lots of interesting complex analysis with spectral curves and all that, Riemann surfaces appearing and trying to understand the systems. And okay, this is maybe a good time to just advertise that if you want to learn more about some of these things, there is a course that I lecture on in SATAX, although actually I saw yesterday on the website that it's not there, so I'm not sure if it's going to be held this year or not, but I think it was my fault because I think I was very slow in proposing it for this year. But anyway, if not this year, it will be available again next year for sure. And where we cover all of these kind of topics, both the classical and the quantum. What I don't cover there, because it gets slightly more advanced, is the fact that these classical and quantum integrable systems are linked in string theory through the ADS-CFT correspondence. So this N=4 theory, for instance, as is well known to have a gravitational dual, that's the Magdalena conjecture. And through this conjecture, if you study magnons in this quantum spin chain, so take a spin chain, you consider some magnons and some excitations, then these are mapped to specific configurations of classical strings on the dual geometry. And of course, in general, this is one thing that is technically true, but perhaps is not very useful as such, because as you know very well, or if you know ADS-CFT, when you're talking about the spin chain, you're on the gauge theory side, that's weak coupling. Here, you're on strong coupling from the gauge theory side, so these don't necessarily they're not in the same space or regime of couplings. However, because of integrability, it has been possible to connect the weak and strong couplings, and for some observables in N=4, calculate, and these are non-protected quantities, these are not BPS states that you expect to have no dependence on the coupling. These are very interesting non-BPS quantities like the Konishi operator and so on. You can find the exact coupling dependence through integrable techniques. Of course, in the planar limit. Okay, one has to emphasize that this only works planar. What I'm interested in is going beyond the standard N=4 story. And there are kind of three, perhaps, main ways of doing this that I'm working on concurrently. So one is looking at N=1 deformations. These are called Lie Strasel deformations, where you change that simple potential we had earlier, this XYZ commutator, to something a bit bigger that's still a conformal theory for particular values of these parameters. That's one thing. I'll say one thing about it later in the next slide. Then more recently, I've been looking at N=2 orbifolds. So that's a situation where you take these fields, X, Y, Z, V is the gauge field of the theory, which I did not discuss, and you do an operation, a discrete operation to it, where you identify these fields with minus themselves, but at the same time, for each of these fields, box means any of these four fields, you act with a discrete group, which acts on the gauge group, which now I'm taking to be the order of this discrete group, gamma times n, so it's a bigger gauge group, and I'm acting with this and this at the same time, and then I'm reducing kind of the spectrum or the kinds of fields to their orbifolded versions. And then you can marginally deform these. I'll say a couple of things about those as well. And finally, you can also add d-branes on the gauge theories, on the gravity side, which corresponds to adding defects or boundaries on the spin chain side. And then you can wonder whether adding those, let's say, boundaries on a spin chain, like having, XXX model, Heisenberg chain, but now with a particular boundary configuration, whether that preserves integrability or not. I'm not going to say anything about this, but Leila, in her talk, I think on Friday, will cover a little bit this topic. Okay, so in N=1, I think I have to speed up a little bit because I don't want to give too many technicalities, but we've been working also with my former student Hector on some aspects of understanding these n=1 deformations. And the main thing I want to emphasize is that what appears here is this concept of quantum symmetries, or what you could call quantum groups, which is a deformation of the usual Lie algebraic structure that we know from group theory. You know, we know what a Lie algebra is, and a quantum group is basically a twist of that structure in a particular, consistent way, which, however, generically seems to break associativity. So the associativity of our usual the way that we act with spin and all that on states is broken in general. And you can now ask many questions about this. Okay, integrability seems to be broken by this, but for the cases which are integrable, which are associative, then there is a technique called TST transformations, which is equivalent, which allows you to get these cases on the gravity side. You can also do something called Yang-Baxter deformations, which allows you also to get these cases. However, for the non-integrable or the non-associative cases, the corresponding statement is not known, and that's one of the things that we're working on. How do you how do you go beyond these simple integrable cases, which are kind of simple twists, very abelian in some sense, to more general cases. Okay, so there is a nice framework called generalized geometry, which I'm not going to explain now, but okay, if anybody has a question, I'm happy to explain how that works out, and we think that that will help us understand the structure. For the n=2 case, these are the orbifolds, then we have more complicated theories which have what this diagram is called a quiver shows you is two gauge groups, SUN times SUN in this case, with various fields. These are bifundamentals, these are adjoints, which are linking these fields. And you can study the various spin chains that come. And one of the simplest spin chains that arise, if you look at the planar limit of these theories, is alternating Hamiltonians. So there's a Hamiltonian like XXX, but the coupling is from ferromagnetic Hamiltonians, so kind of nice, simple, metal models. But the couplings are alternating between even and odd sides. And that's a system that is quite interesting, and not much is known about it. So we studied some aspects of magnons there, and there's been some recent work by some not myself, but some collaborators of mine on the 3 and the 4 magnon problems for these kinds of chains. We also studied the symmetries of these theories, and we did something called a twisted groupoid representation theory. We don't need to know the details of this, but basically what we're trying to say is that this SU4 that naively is broken is still kind of there, but you have to generalize your notions of Lie algebras and to something called Lie algebroids, and Lie groups to something called Lie groupoids, which I'm not going to really explain much, but again, I'm happy to discuss if there are questions. So this is the usual 20 prime. This is one of the standard representations of SU4, and what we're claiming is that this is still there, but if you think in this groupoid sense, if you don't naively, this is broken if you do the orbifolding. There's some current work that I'm doing on more general orbifolds, which gives you even more exotic spin chains, and that's kind of interesting, perhaps even from a condensed matter perspective, kind of interesting. There are some links to some of the statistical models that we're developing, long wavelength limits, something more about the groupoid structure, which again, I don't really have time to discuss. And you can do more. So you can study these spin chains that we get numerically, study their integrability. There's methods which are not reliant on integrability, like the recursion method, or the spread or Krylov complexity kind of measures that can tell you or indicate if things are integrable or not. So we're studying all of these with eventual goal of understanding whether integrability is still present for these. Other work, more going towards the future, and I'm almost finishing, I mentioned this work on integrability for with boundary conditions that Leila is going to say a bit more about. With Vishnu, we're kind of finishing up a paper on something called quiver Yangians, which is also a very interesting integrable algebraic structure, but in this case it's used for something else. It's to count BPS states, or actually to give you the algebra of BPS states. Also, I'm interested in higher spin black holes and modular properties of these black holes. So these are related to thermodynamics of black holes, but in a much simpler setting than the usual one. This is a 3-dimensional black hole, it's not 4-dimensional. Non-planar effects. I don't think I should go through these in detail because of lack of time, but there's quite a few things that if somebody has a question, we can discuss a bit later in the discussion session. In terms of the math that we use, Okay, the main thing that I just wanted to kind of go back to is this notion of a twist. So, if you think of this x, y minus y, x, and you think of x as up and y as down, that's the usual singlet, right, in quantum mechanics. Now, what happens when you go to quantum groups, so this is annihilated by all the generators of SU2. Now you can have a quantum version of SU2 where instead of this, you annihilate this. Where you put a q there, where q equals 1 is the classical limit. Classical, of course, it's still quantum mechanics, but classical from the quantum group perspective. And then you can think of this as a twist of the standard structure, where F is some matrix that acts on this direct products, and then you take them. So if this kind of cryptic thing interests you, then again, you're welcome to ask me about it. But this is how we think about quantum groups, as twisting the algebraic structure, so twisting the direct products. And getting this to be the singlet of your new deformed group. Okay, because I'm kind of out of time, let me just quickly go to why am I doing this? Okay, so as I indicated, so what's the purpose? Okay, is it just because I like these technical things, or is there something more to it? So I believe that there is more to it, because much of what we know, and this is where I'm putting on my string theory hat, about string theory is based on perturbation theory, string perturbation theory, very simple backgrounds, and so on. And many of the puzzles, okay, that's my personal opinion, that we currently have with string theory, like the landscape problem, which has given string theory a very bad name, right, are perhaps possible to resolve if you have a deeper understanding of the dynamics of the string theory. And so I feel that when we're doing string theory, often we are doing the same thing that people were doing when they were talking about atoms before they knew about quantum mechanics, so trying to classically kind of understand atoms, and of course that does not work. You get all these UV problems and so on. So what we need to do, and this is very long term, and this is not going to happen in my lifetime most likely, is we need to understand string theory in more general backgrounds, non-perturbative aspects, membrane dynamics, perhaps M theory, background-dependent formulations. So all of these things are difficult, and that's why very few people are doing them. But to me, studying integrability points to some of the deeper structures that string theory has inside it. So it's a gates theory question that we start from, but by making these connections through ADS-CFT and through understanding the deeper structures, okay, it might be category theory, and maybe we'll have to learn category theory one day. So it might be things that we don't want to engage with directly, but or yet. But it's pointing out that if something crops up all the time in these kinds of attempts to mathematically understand string theory, then maybe we should engage with it. And that's part of why I'm kind of interested in understanding all of these weird algebraic structures. Okay, thank you.
Okay, well, please take them.
All right, I'll break the seal. Maybe two questions. Simple question, what is RR for RR background?
Ramon backgrounds. So this is when you have fluxes turned on from the Ramon sector of string theory. So not the B field or the dilaton, but some of the other fluxes. And they're notoriously difficult to quantize string theory around those backgrounds.
And second question, so thank you very much for this slide, because this is really what I was wondering. So what's the bigger picture in terms of the more...
I mean, some people might disagree with this picture. Maybe other things are more crucial in string theory than these, but that's my personal view, of course.
Yeah, no, but this is really helpful. And as somebody who's more on the phenomenological side, can you see even other sort of applications that are more physically... I don't want to say physically relevant. I feel like that's where my brain is going. But
you see, the thing is, we can always try to do QCD, right, using string theory, right? And then you can make a bottom-up model, and you can get somewhere, right, with hydrodynamics and all that. But I find those to be, of course, they're very useful, but they're effective models, really. And you don't have a well-defined, consistent kind of string setup that you know how to quantize, and how. So you're kind of, picking things from different, which is of course good. I mean, it's part of the intuition that you're building, just not the intuition I kind of are more comfortable with, because I come more from a supersymmetric and kind of mathematical physics direction, like in all of this. So I'm more interested in the mathematical intuition that one gets. But definitely one should not ignore what we learn from black hole information, because string theory, of course, tells us a lot about black holes, and I do not mention it here just because it's not my the topic understand the best, or from the QCD and heavy ion links, which of course string theory is very successful in some sense, but of course things are lacking. We know that these are not true models of QCD, and by a long way, right? So, but so things are definitely, there are many correct things about string theory and what it tries to tell us about particle physics. But I feel that some dynamical principle is lacking, and that's why we get into these kind of crazy kind of cosmological constant problems and all these other things that we should probably try to spend a bit of time at least to understand these dynamical principles rather than just making models. Nothing wrong about models, but
Very good, thank you.
We are running a little bit late. Is there a question online? Sorry.
There's a question online.
Did
You want me to read that?
Please, that'd be great. Thank you.
All right. It says, does breaking the integrability mean the necessity of introducing numerical approaches, and which ones, for example?
Yeah, so it's not necessarily numerical that you have to do. Of course, numerics can play a big role when integrability is broken. But I did mention this recursion method at some point, which is not really a numerical method. It's an approximate method, but it's an analytic approximation method where you can do some partial fraction expansions and eventually cap it off at some limit where you reach the accuracy that you want. So you don't have to necessarily go fully numerical. But yeah, there are many other ways. Okay, one thing I did not mention, well, it is one of the slides I kind of skipped at the end, is these approach where also PALLAB has worked on in the past on analytic methods for understanding non-integrability, like proving non-integrability for a classical system. And that's also part of it. So yeah, you don't have to necessarily be numerical.
There's one super quick question because we're very late, but you had a quick question and a quick answer.
I have a question.
Oh.
Okay, wait.
Just a discussion later.
Okay,
We can do it in the discussion.
there's quite a bit of time, so thanks, Kostas. All right, next. Maybe while you set up, Anush can ask this question. No,
Okay, thank you. So Kostas, my question is, you showed a deformation of n equal to 1, sorry, n equal to 4 to n equal to 1.
Yeah.
Is that the same as n equal to 1 star deformation?
No, not exactly. So n equals 1 star, well, the standard n equals 1 star is a massive deformation. So you turn on some masses, and then you follow it to the kind of conformal point, like to the infrared. This is a marginal deformation, not a relevant one. So this preserves fully superconformal invariance yeah. So n equals 1 star is also, of course, a very interesting theory, but in terms of integrability, the way we understand it now, we want the superconformal part to be there because we understand through the dilatation operator of our theory. Yeah.
Okay, the last talk before lunch is your commissioner from this. Thanks. I'll give you 5 minutes.
So this talk is either going to be optimistic or pessimistic, depending on your view. But I think the way we do physics and mathematics is going to change, and we need to adapt. So this is my take on this problem and what I think will happen. So we have these new computational tools, and these new computational tools will be addressing. But maybe it's important to reflect on how these tools came to be and how they're useful in mathematics. So computers and mathematics, their utility was established in mathematicians essentially by solving two very hard problems. The first is the classification of the finite simple groups. There are 16 infinite families of such groups and 26 exceptional groups, the largest of which is called the monster group. And the classification of this work of these groups was initiated by Galois. So this was 19th century mathematics, and it was completed in the 1980s. And the proof is still being written up and formalized in books right now, but people believe we have classified the finite simple groups. And to write down character tables for some of these exceptional groups, we required computers. So the first sort of instance of computers being crucial to mathematical discovery. The second sort of instance was the proof of the four-color theorem. So to color a map on a plane, on a sheet of paper, you need no more than 4 colors in order to ensure that adjacent boundaries are colored differently, and there's no confusion as to which province you're in. So this, again, this was a proof by exhaustion by Appel and Haken. They essentially determined all the possible kind of boundaries you can have in a map, and they show that each of these can be colored with just 4 colors. So this is sort of the first big proof in mathematics that also required computers in a crucial way. So this is the starting point. We don't have a similar instantiation of such an important problem that modern tools have solved. So one of the goals in approaching machine learning methods, for example, in mathematics, is to come up with an important problem of this caliber that you need these new tools in a crucial way to address. So the biggest result so far, I would say, in applying AI to mathematics is the discovery of what are called murmurations. So if you look at birds that are flying around, you sometimes see these patterns in the flocking. This is called a murmuration. And it turns out if you do certain averages over elliptic curves, you see a similar pattern arising. So this was discovered using neural networks. And Hay and collaborators were able to establish this pattern of murmurations as a phenomenological discovery regarding elliptic curves and L functions. And then mathematicians got excited and they proved theorems based on this observation. So I would say that of the discoveries in mathematics that are AI informed, this is the biggest one so far. The area that I've worked in applying, I'm not one of the collaborators, no. Although I do work with one of these authors, I'm not one of the collaborators on this paper. So I work in knot theory sometimes. I dabble in this, and I use machine learning methods in knot theory. So rather than give you a seminar, I'll just summarize the result. There are certain invariants of knots that are polynomial invariants. So no matter how you draw a particular knot, you always get the same polynomial invariant that you compute. And there are other invariants that are numerical invariants. And for a class of knots called hyperbolic knots, there's a volume associated to the complement of the knot as an S1 embedded in an S3. You take the complement, you find some number, and the number is independent of how you draw the knot. So it turns out you can predict this number, this volume, from the coefficients in the Jones polynomial. And this was an example of using a neural network to predict this volume with about 2.5% error, which for reasons I won't go into is about the best you can expect on this particular problem. So we're able to make this prediction using neural network. We want to understand how this prediction is made. So, well, there's a slide here on neural networks. I can explain any of this to you if you want, but let me just imagine that because Hopfield and Hinton won a Nobel Prize in physics for these kind of tools. You've seen this slide before in some other talk, and I won't go through these details. But neural networks are a way of making these predictions. This is the tool I'm using to make the predictions in the previous plot I showed you. Okay, so we want to explain these discoveries that we've made. Why is it the volume can be learned from this polynomial, the Jones polynomial? And we basically used a tool called layer-wise relevance propagation, which assigns a relevance score each neuron and each input feature. And these are sort of colored in. And it turns out that whatever knot you look at, the different knots or the different columns, the same feature is colored in. The same feature is the most strongly relevant in making the prediction. So based on this observation that there's a strongly relevant feature, we're then able to come up with an analytic function which approximates the behavior of the neural network. So this function does about as well as the neural network I showed you, roughly the same error in making a prediction. And we can interpret this in terms of what's called analytic Chern-Simons theory, something which Witten described in understanding certain invariants that appear in knot theory. So we're able to, in this particular case, to translate our observation about knots, which was machine learning derived, and then come up with an explanation in terms of physical theory that we sort of understand. In some ways, it's the simplest non-trivial quantum field theory that's doing this explanation for us. So this is a case in which we can take an AI discovery and come up with some physics and mathematics that underpins this discovery. And we actually do more of this, of course. We want to see whether we can translate correlations we see in data sets to things that are physical about those data sets. And other people have a similar idea. There was this DeepMind group that Davies was the first author on this paper, and they essentially use similar features. Instead of using layer-wise relevance propagation, they used the saliency analysis. They figured out that in feeding lots of inputs in your neural network, these three big features are the most important. And from looking at these patterns, they conjectured this theorem, which they then proved. So a fellow named not going to be a knot theorist was on this paper, and he's I think the one in this collaboration who came up with this proof for a theorem that was obtained by looking at machine learning results. So there's also been lots of other work in knot theory. Knot theory is one of the simpler areas of mathematics that's machine learnable, and other groups have played with different aspects of knot theory as well. So it's a good playground for investigating the confluence of these ideas of machine learning, mathematics, and physics. Okay, so what's a big problem we can study? And this is one of the big problems that I'm after. And I think now is the time to be ambitious. So just like, computers established a role in mathematics by proving these big results, this is my big result that I'm after. It's called the smooth Poincare conjecture in 4 dimensions. So last of the Poincare conjecture is still standing. It basically says anything which looks like a sphere is a sphere. And it turns out there are different ways of phrasing this. There's a smooth Poincare conjecture for homeomorphic correspondences, for piecewise linear isomorphic correspondences, and for diffeomorphic correspondences. These are defined here in case you don't remember what these definitions are off the top of your head. But the idea is that in every case, it turns out that the homeomorphic statement is true. We have a map from X to Y that's 1 to 1 and onto, with F and F inverse being continuous functions. Such a map always exists from a homotopy n sphere to the normal n sphere, independent of the dimension. But the other statements are dimension dependent, and it turns out that the piecewise linear isomorphic case is true for all n not equal to 4. For n equals 4, we don't know the answer. And that's why this is the last of these conjectures that are still standing. N equals 3 case famously won Parliament Fields medal, which declined maybe 2006, maybe 2 decades ago already. So all of these results are basically about spheres, one of the most fundamental objects we encounter in mathematics. And we don't know something about 4 spheres, which seems to be a major lacuna in our understanding of very simple mathematical objects, which is why this is an interesting problem. So the problem is related as well to what happens for 7 spheres. So the diffeomorphic part, the diffeomorphic statement of the smooth Poincare conjecture, that's false generally, but it happens to be true in these dimensions. We don't know the answer n equals 4, n equals 7 is the first dimension in which it fails. It means there are 28 different things which look like a sphere, but are distinct as far as their differentiable structure goes. And the simplest one of these is to interpret a 7 sphere of this type, which is not normal 7 sphere, as an S3 bundle over S4. So you can make these things rigorous, and there are these exotic spheres in 7 dimensions. So the question is, are there exotic spheres in 4 dimensions, which is the content of this conjecture? Now, the reason why this is interesting from a knot theory perspective is that if certain knots have certain properties, they provide counterexamples to this smooth Poincare conjecture. So you can construct a knot with a certain set of properties, you're able to establish the falseness of the statement. And using neural networks to predict certain non-invariants, in this case, the S invariant of the slice genus, you can ask me about if you're interested. We can predict these using neural networks from polynomial invariants, and this may identify counterexamples, potential counterexamples to study more carefully using traditional methods in topology. So this is an avenue I'm exploring in addressing this important problem in mathematics. But using AI in mathematics, we find there's certain areas of mathematics which are machine learnable. So topology is a case study I told you about. I've also looked at algebraic geometry, group representation theory, finding numerical solutions to things like metrics and Clavier spaces. We can address all of these problems with AI in natural ways. Other areas of mathematics like number theory and analysis are much harder. And there hasn't been much progress in these areas of mathematics with these new tools that are available so far. One thing we've seen is that there's a Moore's law-like statement you could make about the improvement of AI. So I've taken this plot from a paper by Douglas and Verstwick, and what they see is that if you look at how fast if you have some measure of how good AI is, this it improves by doubling in performance every 2.5 to 3 years. Whereas the number of papers, the number of patents, these double every 10 years. So this is a very, very rapid progress in this area. And the green dots here are the strength of chess engines. And we see that the chess engines are also increasing with roughly the same slope as the improvement in AI. So yeah, the thing is, you notice every 3 years you're doubling in strength. So this is pretty incredible. So we have a new pipeline, and this is maybe how we'll do mathematics in the future. The state of the art currently is neural networks can efficiently learn correlations in large data sets. Then there are ways to extract conjectures automatically from looking at various examples. These conjectures are putative statements of theorems, which you can maybe then prove. Then AI is created within certain restricted frameworks like chess and Go, and you can axiomatize the rules of the game like mathematics, and maybe AI is creative in those contexts as well. The state of the art currently is that elementary proofs written by machines are indistinguishable professional mathematicians from graduate student written proofs in graduate courses. So that's how good machines are today. So they're not good enough at creating a new idea, but they're good enough at applying old ideas. And their new techniques, new software like Lean, which check the veracity of your proof, is something which you can take to the bank. So field developers are starting to use Lean in order to establish that their proofs are correct proofs. And this is the Lean code for the Pythagorean theorem. So it's somewhat complicated. And it turns out that if you apply, well, we're working on formalizing the proof of the Fermat's last theorem as well right now. It's one of the projects in Lean. And it turns out this is an interesting observation, because if I was going to prove square root 2, the 2 to the 1 over n is irrational, I would make statements about even numbers to do this. So this is our first proof without proof by contradiction that we learned in elementary school or whenever. A machine would do this differently. A machine would use the most powerful tool in its arsenal. So it would take this expression here, raise both sides of the nth power, say 2q to the n equals p to the n is what this, assuming not the statement is false, implies. And this is just contradictory of Fermat's last theorem. So this is a very, very heavy hammer to hit a very trivial nail with. So machines may not be teaching us intuition, even if they're proving results. And that's something to worry about in the future. As well, mathematical search engines and large language models have entered the game. And large language models write mathematics fluently, and large language models code better than you do. So using these tools, we can maybe come up with a new approach to doing science. So I'm just going to conclude. The question we need to address is, how do we efficiently collaborate with Silicon colleagues? And my prediction is that in the next 10 years, the best physicists and mathematicians in the world will not be human. It'll be a machine. And we need to address how we do science in this context. So there's a famous novella from the old Pulp Fiction days by Jack Williamson. It's called With Folded Hands. And it's a very prescient sort of science fiction story. It tells us about AI, basically. And these humanoids, robot AIs, take over everything people do. And people just sit around at home with folded hands because there's nothing else for them left to do. And this is maybe where we're heading in mathematics, that machines will do the important mathematics, and we're just stuck watching them. So this could be the end of the story as we have. Thank you.
Yeah, just about me.
Yeah, it is, yes. People have been working on this kind of thing, yes. I don't know what the progress is. People have been certainly, machines are very good at coding these days. So they're trying to apply these machines to generate Lean language for various things. Currently, the undergraduate curriculum has been coded into Lean and at Imperial College, and people have verified that what we teach our undergraduates is consistent and correct.
Okay, so we're
Yeah. You first started off your motivation, you spoke about how computers were used to sort of in the last stages of the proof, in the actual proof. And then when it went to AI, it was more like sort of humans were finishing the proof. Do you sort of see AI taking on the role of actually doing full proofs in the future, or is there
I think so. I think these technologies are advancing so quickly that, you know, within a decade, easily within maybe 5 years, we'll see, you know, machines are capable of doing mathematics the way humans are capable of doing mathematics. And then 5 more years, we'll see them being better than we are. That's my prediction. I could be off by a factor of 2, but I don't think I'm off by more than a factor of 2.
So it's the collaboration we propose. I'm just blind. What do you see?
I mean, initially, I think that we need we need to help machines along, and that it can maybe give you 100 true proofs of 100 statements, but are any of them interesting? I think the filter that we apply initially is to decide what the interesting mathematics is and try to point the machines towards that direction. But, you know, again, I think eventually they'll supplant us. So maybe in the end, we just sit on our universal basic income and drink wine and, you know, play recreational physics. People play recreational chess. You know, chess is still, grandmasters still make a living playing chess, even though machines are better than them. So I think there's still a place for us to do what interests us. And at some level, we're interested in knowing the answers to how things work. And for me personally, I don't really care whether a machine teaches me how the universe works or same as physicists teaches me how physics works. I'd like to know the answers to certain questions, and you know, maybe this is a tool to get there.
Not necessarily, but yes, when we are trying to machine take over and then we relate. And the other question might be, how are we going to be accountable? How are you going to account in terms of the quality?
Well, I think the stakes in mathematics and formal theoretical physics are pretty low. So it's not like we're letting AI decide War and Peace. But I think AI will also do that. So I'm more concerned about the ethics of AI in those places than I am here. I mean, here we're wrong. We just figure it out later. The answers, the questions will still be there. Whereas the consequences of being wrong are more dire elsewhere. I don't have a good answer to this. I don't think anyone does. But here, I think you know, if we're steered wrong in the mathematical direction, that self-corrects.
Let's take a minute to close the conversation. Back here at 2:13 for structure.
So I don't know if you know the answer, but I guess there's lunch, and then we all have lunch.
Yes, I believe so.